A little bit more on statements and truth tables. A couple of things that we didn't see last time. The first thing that we're going to look at is a contradiction. And here's the definition. A compound statement is a contradiction, or sometimes our text uses the term self-contradiction, if it is false for every combination of truth values of the simple statements that make up the compound statement. So in all possible cases, if the compound statement is false, then it's a contradiction. And let's look at the simplest form of a contradiction that there can be. Made up of the simple statement P and not P. Let's do the truth table for this. P can either be true or false, and since P is the only simple statement that makes up this compound statement, we only have two truth values. Now we also need the truth values for not P, or the negation of P. The negation sign changes true to false and false to true. And now I guess we're ready for the whole statement. P and not P. And do you remember what the special case of an and is? An and is only true when both of the statements that make it up are true. Well, let's see. P and not P. They're not both true here, and they're not both true here. So it's never the case that P and not P are both true at the same time. So this statement, this and statement, can never be true, because the simple statements that make it up are never true at the same time. So this is going to be false and false. And this is the truth table for the statement P and not P. For all combination of truth values of the simple statement P that makes it up, this compound statement is false. It's always false, so it's a contradiction. Well, let's get into something a little less trivial now. Let's try this example on for size. Determine whether the statement P implies Q if and only if P and not Q. Determine whether this is a contradiction. Now, in order for it not to be a contradiction, it just has to be true for one combination of the simple statements that make it up. And let's see, we have P, Q, P. Okay, we only have two simple statements that make this up, P and Q. So our truth table covers four possible combinations of truth values for P and Q. And remember how we do this for two simple statements? True, true, false, false, and then true, false, true, false. We've set up the truth table to determine the truth values of this statement. Now, what should we do first? We can do what are in the parentheses first, either set of parentheses, This parenthesis requires that we do the truth values of not Q. So I think maybe we should do this first and just put the truth values for not Q right next to the truth values of Q. And the negation sign just flips all of the truth values of Q. True becomes false, false becomes true, true becomes false, false becomes true. Now I guess we can do either of the expressions in the parentheses. Since we just did not Q, we can do this one. P and not Q. This is an and statement. And so we want to remember, what is the special case for an and statement? The special case for an and statement. Isn't it that an and statement is only true when the statements that make it up are all true? So when both of these statements are true, the and statement is true, and it's going to be false otherwise. So we'll look for P and not Q both being true. No, not here. But here we have it. Not here and not here. Okay. This is the only case where P and not Q are both true. We put true here. Everything else is false. Well, we got that one done. Now let's do the statement inside the parentheses here. P implies Q. This is an if-then statement or a conditional statement. What's the special case for an if-then statement or a conditional statement? The special case. Isn't it that a conditional statement is only false when we have a true implying a false? So we're looking for P true and Q false. Do we have it? Yep, right here. P is true, Q is false. And that's the only time that P is true and Q is false. So the statement is false when P is true and Q is false. All the other times it's true, we don't even have to think about it. We have this statement figured out, we know its truth values. We have this statement figured out, we know its truth values. We're ready to do the whole statement. This didn't take long at all. P implies Q if and only if P and not Q This is an if and only if statement. What's the special case for an if and only if statement, a biconditional statement? A special case. What's the special case? Do you remember? A biconditional statement is only true when both of the statements that make up the biconditional statement have the same truth value. So this will be true when both statements are true or when both statements are false. And when does that happen? Let's look. They're not both true here. 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 Okay. These two statements are never true simultaneously. And are they ever false simultaneously? Not here, not here, not here. They're never false simultaneously either. So this statement is never true, because these two things are never true simultaneously, and they're never false simultaneously. So in all cases, this statement is false. Ha ha ha. Okay, it's always false. Always. So we can remark here, since the statement, and I'm not going to write it out, but since this statement is always false, it is a contradiction. Cool. Well, we looked at the contradiction, which is always false. Now here's its counterpart. We call it a tautology. A compound statement is a tautology if it is true for all combinations of truth values of the simple statements which make up the original compound statement. So in other words, a compound statement is a tautology if it's always true. For all combination of truth values, it's going to be true. When we started with the contradiction, we came up with a simple example. Can we come up with a simple example for a tautology? Let's see. Let's try to make a tautology using just the simple statement P, okay? So we have P, and P has one of two truth values. It's either true or it's false. Now, what do you think I'm going to do to get a tautology, something that's always true? Let's negate P, just like we did with the contradiction. But this time, instead of doing a conjunction or an and, let's do an or, okay? So the negation changes the truth values, true to false, false to true. And here's the statement that's going to be our tautology. P or not P. And it makes sense that this would be a tautology because remember the definition of a statement? It's a phrase or a sentence that's either true or it's not true, but both. So P is either true or it's not true. And when it's not true, its negation is true. Now, this says either P is true or it's not true. It's got to be true, right? All the time. But let's use the properties of an or statement to show this. What's the special case for an or statement or a disjunction? The special case for an or statement. The only time, think about it. Do you remember or statement, the special case? The only time that an or statement is false is when? When both statements that make it up are false. So whenever P and not P are both false, this thing's going to be false. Does that happen? Well, here's true and false. P is true, not P is false. Here's false and true. P is false, not P is true. These two things are never false at the same time. So the special case for an or statement where they're both false can't happen in this case. So there are the truth values for this statement. This statement is always true. This statement is a tautology. Now let's take a look at something a little bit more complicated. Okay, something with a little bit more substance to it. Determine whether this statement, P implies Q, or Q implies P, is a tautology. And maybe I can read that differently. I read it correctly, but there's a different way to read it. If P then Q, or if Q then P, is a tautology. Now we only have two simple statements. We have P, we have Q. So there's only going to be four combinations of truth values. And remember the way we do it? On the outside, true, true, false, false. And on the inside, true, false, false. I guess we do what's in the parentheses first. We can do this. If P, then Q. Then do that. If Q, then P. And then we'll do the whole thing. So P implies Q, or if P, then Q. This is an if-then statement or a conditional statement. What's the special case for a conditional statement or an if-then statement? What's the special case? The only time that this is false is when? When we have true implying false. So we look for P equal true and Q equal false, and here it is. And this is the only time that it happens. This is the only time that P is true and Q is false. So this is the only time that that statement is false. It's true all other times. Now, let's do this guy. Q implies P, or we could say, if Q, then P. And again, this is a conditional statement, an if-then statement. What's the special case for an if-then statement? It's only false when we have a true implying a false. So now we look for the case where Q is true and P is false. And that happens right here. This is the only time it happens. Q is true, P is false. So the the statement is false under those circumstances. For all the other cases, it's true. Now, I guess the only thing to do now is to join these two things together with an or statement. P implies Q, or Q implies P. So in the broadest sense, or the most general sense, this is an or statement. It's this thing or that thing. What's the special case for an or statement? An or statement is only false when both of the statements that make it up are false, right? So when both of these things are false, the whole statement is false. Now, where does that happen? It doesn't happen here, they're both true. It doesn't happen here, this one's true. It doesn't happen here, this one's true. And it doesn't happen here either, they're both true. So there's never a case when this statement and this statement are false simultaneously. But that's the only time when an or statement can be false, is when they're both false simultaneously. Since that can't happen, this thing is true under all circumstances, and son of a gun, this is a tautology. It's true all the time. It's always true. So this is a tautology. Excellent, excellent, excellent. Now, there's one more thing that the book talks about that I need to define. The last thing that we're going to talk about is something called an implication. An implication is a conditional statement, an if-then statement, or this implies that statement. It's an implication exactly when it's a tautology. Now, in all of the cases before, when we did the contradiction, when we did the tautology, we created a really simple example first. So let's do that again. One simple statement, P, and we want to create a conditional statement, an if-then statement, that's always true. Well, let's see. Will that do it? P implies P, let's see. It's an if-then statement or a conditional statement. So when is the only time that it can be false? It can be false exactly when we have true implying false. Does that happen here? In this case, P is true, so we have true implying true. No, that's not going to be false. And in this case, we have false implying false. It's never the case that we have false implying, I'm sorry, it's never the case that we have true implying false. So this statement is always going to be true. And son of a gun, here's our implication. It's a tautology, it's always true, but since it's of the form if then, it's also an implication. It's an if then or a conditional statement that's always true. Now that was a cheap trick, but we wanted to see a really simple example of an implication before we go a little bit deeper. And now we'll create, hopefully, a statement which is an implication and one that has a bit more substance to it. This one might do the trick. It's definitely a conditional statement. It's of the form if this thing, then that thing, if then, or we could say this thing implies that thing. It's a conditional statement. So if it turns out to be a tautology, then this thing will be an implication. It's a conditional statement. If it turns out to be a tautology, then it will also be an implication. So let's do the truth table for this thing. And let's do P and Q first. This is an and statement. What's the special case for an and statement? An and statement is only true when what? Both the statements that make it up are true, right? So when both P and Q are true, this thing will be true. And that only happens here. P is true, Q is true. Every other time, at least one of these is false. Okay, so we got P and Q. Now let's do the statement P or Q. This is an or statement. An or statement. What's the special case for an or statement? An or statement is only false when? An or statement is only false when both of the statements that make it up are false. And where does that happen? It only happens here. P and Q are both false here, and that's the only time it happens. Here Q is true, here P is true, and here they're both true. This is the only case where they're both false. So this is when P or Q is false. Every other time the statement is true. So we've done P and Q, we've done P or Q. Now we can do the whole statement. This is a conditional statement. If this, then that. Or we could say, this implies that. What's the special case for a conditional statement? The special case for an if-then. A conditional statement or an if-then or this implies that, it's always true except when we have a true implying a false. So if this is true and that's false, the statement's going to be false. Now, where does that happen? Well, let's see. This is the only case where P and Q is true. And P or Q is true at the same time. It's never the case that P and Q is true and P or Q is false. That doesn't happen. So we never have true implying false. So this is going to be true all the time. And son of a gun, our unbeaten streak continues. This happens to be a conditional statement that's a tautology, so it's also an implication. Excellent, excellent, excellent. Well, I guess we're going to finish the rest of the homework in section 3.3 now. I will send it out.